Yeah, hi everyone. Welcome to Pandas 1. So this is another Python library which is extensively used in data science. Um, so this is also used. This is also, this is also similar to NumPy, but this is way more feature rich than NumPy. So this is the agenda for this class. Let's go with the first one. Why do we need Pandas now? So Pandas works with actually NumPy is only for homogeneous data, while Pandas can work with heterogeneous data simultaneously. Although we did see how like we can set the type as data type as object in NumPy, and we can still work with heterogeneous data, but you won't get the type of features that, or rather the methods that you have in Pandas are far more powerful and far more versatile. So if you look at the first reason why we use Pandas over NumPy is it is really good with tabular data. It's super easy with tabular data. So you have tables like rows and columns, right? In the NumPy equivalent for this would be a 2D array. You have a 2D matrix. You can create some values, but you'll face severe limitations. Like you cannot access individual columns based on names. We'll see the features in the upcoming sections, upcoming sessions. So one of the advantages with tabular data is you have really nice output. You can see the output in a proper tabular format. It's easier to use, and supports we can work with multiple data types at a time. We can also, again, the second advantage is labeled indices. So in NumPy you have standard 0, 1, 2, 3, 4, 5. The indices are set. You cannot make any changes here. But in Pandas, what you can do is you can create. You have your typical integer-based indexing from 0. You can also reset, reassign indices from, like if you don't want to work with 0, 1, 2, 3, you can set it from. You can start your index range from 1 to n. You can also create indices with strings. So you can, if you don't like numbers, you can do with A, B, C, D, E, F, G, like A to Z you can give. You can also give floating point integers, floating point indices like 1.0, 2.0, right? And if all this is not good, you can also create a column. So if you have a column, say something like invoice number, so it has some so the one of the values is 1, 2, 3, 7, 8, W, 6, F, again like maybe 5, G, A. You can assign an entire column, you can set an entire column as an index column. So we can access rows based on these invoice numbers as well. So you can set custom labels. So this is called label-based indexing. The other reason why we use Pandas over NumPy, or why rather Pandas is super convenient, is missing values. So if you have like a million rows, suppose 1 to 1 million, and you are bound to have some missing data, right? So suppose 50 or maybe 3000 values are missing. What Pandas allows us is it gives us special methods like PD, and we can select the column name, and we can check is null, or we can check we can do fill NA, which is fill the missing values, and we can set any missing value, and that will automatically fill these all 3000 values. But in NumPy you don't have that feature. It will simply set the value as NA, not a number if it's a numerical value. And if you want to fill these 3000 values, you'll have to do it manually. That's a huge pain. So that is one of the major advantages in Pandas. The other advantage is broadcasting or alignment. I think this sits better if I show it. So before I show the example, let's just do the installation. Pip install numpy. So we use this exclamation mark for Jupyter notebooks, otherwise just pip install is fine. Requirement already have this stuff, so just to see our version. So we have numpy version 26.4, PD version 2.2.2. So this is just to verify it's properly installed. Now, numpy broadcasting, or rather numpy alignment, the way it does is, let's take two numpy arrays, np.array 1 2 3 and 10 20 30. So if we do a plus b, what you will see is it will do a element by element arithmetic operation. So suppose if your data is messed up in the b array, if it is this way, then what it will do is it will do an addition with the messed up values. The advantages in Pandas is you can actually specify the indices, like we saw labeled indices, and it will only check if the indices are matching and then perform the operation. So so we do pd dot, we take a series, so it is similar to numpy array. It's like the equivalent of a vector in Pandas, and we take the same and we can assign custom indices to this. So I will take A, B, C. So if I don't specify the indices, the series will take the usual 0 to n based indexing. But if I assign custom indices, you will see the indices change to these custom indices A, B, C. And I can, and if I do the same for B and give a 10, let's take this messed up example itself. So now our positions are not exactly correct. So, and if I change these values to this, suppose, and if I add both of them, you will see they matched the indices exactly and then added them. So okay, let me take this as x and y just to get rid of the confusion. X plus y. So the x series had index 1 at index A, but the y series has 10 at index A. So it properly matched that and then did the addition. So even if your indices are messed up, it will still safely, properly do the operation. The other advantage is, suppose I don't have index B, I have index D, and I have index E. So if I do an addition, if you see the output, there is no A index in the Y series, and since it could not find the appropriate index, it just avoided the operation. It did not throw any error or any such sort, any such thing. So B is also missing in the Y array, so that also gave an NaN. But C is present, so it properly matched the C index and then performed the operation. Same with D and E. So that is the advantage of Pandas alignment. It will properly check and then perform the operation. So that is broadcasting. So the other advantages, data science tools. NumPy is basically bare bones. It is really good with numerical operations and pure math operations, and it's super fast. It's actually almost, you can say, twice as fast, which we'll check right now on a million rows. But it does not have specialized methods, like it's not feature rich. So it's like you have an iPhone, but you don't have the apps. For example, you have data science tools like something like grouping. So suppose if you have a table with let's say multiple categories. So you have different types of cars, right? Let's say you have SUVs, you have hatchbacks. Excuse me. So you have SUVs, you have hatchbacks, you have sedans, right? And there are multiple categories of these cars in your table. So what grouping does, if you group by this, what is this called, car, let's say car type. If you group by car type, it will create separate tables for these groups. So you'll have all your SUV cars in one table, you'll have all your hatchbacks in one table, then you'll have all your sedans in one table, and then you can perform various operations, like you can count the number of things, or you can check the mean of their speed or range, or you can perform many other operations. So that you have grouping. Then you have time series, which is one of the core advantages. Basically, you can manipulate dates, right? You can add 7 days to the date. For example, if you want to switch, what is it called? If you want to extend all the dates to +7, like the next week, you can perform that on all the rows. Or if you want to change the time zone of these dates on all the rows, you can do that. Rolling average. What else? Date ranges. You can set the date ranges based on this one, or you can extract the year or month or date from these dates if they are in the correct format. So you will have many such tools. You can do merges as well. You can merge two tables based on a particular key value. So for example, let's say you have let's take a very common example. Let's say you have a table with users and their respective professions, right? So you have user ID 1, 2, 3, 4 and another UID 1, 2, 3, 4, but in this place there are professions. So it's a web developer or a crypto guy or an Android guy, etc., and you have names here, like maybe Priya or James, etc. So standard NumPy, what NumPy will do, if we want to merge two tables, NumPy will simply stack one by one, like it'll just stack them together without any, you cannot specify any condition. So suppose these user IDs in professions, these are messed up. So suppose this is 3218, suppose these are the user IDs, and in the names table you have 1, 2, 3, 4. If you stack them horizontally 1 to 1, you will get wrong info, because now the user ID 1 is Priya, and the corresponding row in the professions table is data related to user ID 3. It's not related to user ID 1. So you will get completely wrong data in this case. But Pandas allows us to merge the tables based on a condition. So we can say if user ID equal to 1, so suppose this is 1, so then we merge the table based on the condition. So 1 Priya and the appropriate profession, and then 2 whoever, James, whatever particular profession, 3, so on and so on. So you can actually merge the data in an intelligent way. So that is the other advantage. And the other, like another major advantage is IO operations, rather the IO what is it called, the ability to load various types of data. So if you look at the, let's look at the methods that Pandas provides. These are all the methods that Pandas provides. If we check the type of input availability, so we can read data from clipboard, we can read from CSV, we can read from Excel, we can read from, I don't know what this feather even is, we can read from HTML, JSON, the standard ones, right? These are all the famous ones. We can even load the SQL as well. We can take SQL files as well. So we have tons of input options, so we can load all these files and create tables. But if we check NumPy, there's barely any options. So in fact, although there's a lot of numerical operations, we only get gen from text and few others. So I think we also have, I think there is another load text. So only txt files and probably one NumPy files as well. But these, like, you have very few options. So let's search for CSV. So there is rect from CSV, but let's check JSON. There's no JSON. There's no Excel. There's no SQL. So as you can see, it's severely limited. Okay, so just to show you how how we load files in NumPy and Pandas, I'll just give a small demo. So we can do something like data equal to np dot. The method was gen from text, gen from txt. Let's check the documentation once. So obviously we have to give the file name. For now, we'll take the sample. We'll take a small sample, or rather, we'll load this file just to see what is the issue with NumPy, why we face, or rather, why Pandas is far easier than NumPy. We'll have to load the file name. Let's check what's happening. Some errors were detected, so we'll have to specify other arguments as well. We have to say something like, yeah, we have to specify data type. What happens is, NumPy, as you know, is meant for, it's primarily meant for numerical computation, and it works on homogeneous data. So if we are trying to load this this file, which is, if you see, it has strings, it has integers, it has floats, right? So what happens is, it'll not work unless we specify the data type as none here. So it'll consider all the data types, and then we'll also have to give the delimiter, because we are working with CSVs, comma separated files, and let's see, it says got 7 columns instead of 6, so I guess we'll have to specify, we have to specify the names to use the columns, to use the column names. Names is 0, I guess, and then let's see, what is the names functional? Names. Okay, we have to give a boolean. Names is true, we have to use the names, and then we'll also have to specify encoding, but I guess we can skip for now encoding. Let's see, but on this one, missing values. So we can set, so what this is, it does not mean we can set missing values. What this says is, if you find any of these missing values like empty, or if you see something like NA or NA, it will identify these missing values, and then if it is a numeric type, it will set it as NaN, and if it is a string type, it will just leave it as empty, like it will just keep it as empty strings. Let's see, will this work? Still no. What? As you can see, we are facing a lot of issues for just loading the file. What else? Delimiter, converters, missing. Let's take encoding. UTF-8. Still no. So what it's saying is got 7 columns instead of 6. So I guess there is there's some value missing in these places. So line 230, 326 and all these places. We don't want to go through all that. Let's try loading a sample. Let's try loading a smaller version. Now if you see the smaller version loaded, even though it has some missing values, if there is a missing value at the end, that is where NumPy is getting NumPy is facing issues. We can now this is just a smaller version, and as you can see, we are facing like a ton of problems. Now if I try to access some value, say country, I can access values based on columns, but this is very tedious process. Now if we try to load the now if we use pandas, let's say pd dot, we use read CSV as we saw here. We have ton of options, right? So we are using read CSV, so we are using this option, and I load the original file. So I take gdp.csv, it loads all of them. So we have 1703, and as you can see, it's a pretty simple process, just one line of code. I don't have to think of other options, and so basically these are the major reasons why we use pandas. Now let's look at why NumPy, we might want to prefer NumPy over pandas in what cases, and the primary reasons we use NumPy over pandas is basically if you are doing pure math or numerical computation on homogeneous data, then it's actually quite fast. So let's look at the speed test ones. We'll take the same example. Let's see it. take large data. So you see this GDP file is only 84 KB. Let's take this sales data, which is 94 MB. It has, I think, if I'm not wrong, it has more than a million records. Sales data, and I don't think we won't be using all this. It is a CSV, so we'll use this delimiter. This is unnecessary. What are the other options it has? Just give me a moment. We'll skip the header because we'll check the mean. Skip header true. I think skip header is true. No, skip header should be 0. We want to skip the column, these values, the top row, which is the column labels, and then we will before that, I guess it's better to load the sales data here and check yeah, we'll do an average on quantity or price. We'll do an average of this one, and we'll check the time on 1 million rows. So if you check the number of records we have, 1 million. So 1067371. Okay, let's get back to this one. What is it? So we will select columns here. Yeah, we'll use this argument, use columns, since it's really painful to load the entire file. We'll load a single column and we'll use a mean on that. So 0, 1, 2, 3. Let's take quantity. Okay, so fortunately that is loading properly, although there are some missing values, but 12, 12, I guess it's loading properly. Let's do a slice, top 10, 12, 12, 12, 48, seems to be working, seems to be correct. So we have the slice data. Let's do a mean on, okay, we have the column data for quantity in NumPy, speed test NumPy. Let's do a mean on this, so time it. Data dot mean. Let's see how long it takes. So it took 223 µs microseconds, plus or minus 2.68 microseconds, which is the standard deviation. So the way you read it is, this is basically, it ran this code 1000 times, and it did this in 7 batches. So it did a 7000 loop test on this code. So it ran this code for 7000 times. It runs. So one might ask, like, why do we need again? Why do we have to do 7 runs when you already did this 1000 times? So so this is related to the CPU. It is related to CPU things. So every cycle there is some. It takes in a batch and then performs just to get robust results, so that there are no false positives, or like there's no false data, like just to avoid that, or rather just to make it more clear, it runs this code 1000 times, and then it does it for 7 batches, and so it computed the average as 223 microseconds. Now let's do the same thing, speed test on Pandas. We'll take the same code, and we'll do a mean on mean on the column which is quantity. So one of the advantages is obviously we can do the same in NumPy as well, but as you saw, it's a huge pain to handle missing values, and it's a huge pain to load the CSV itself. Just imagine doing this on 1 million rows, and there are like 3,000 missing values you'll have to handle manually, going checking each and every row in that every missing value in those rows. So we'll do a data, and we'll extract the quantity. Let's just do a head. Head is basically top 5 rows. So we have the quantity data, and then we'll do a mean on this quantity column. If we do a % time it, so not that, I mean, you could say it's kind of slow, right? So it's 349 microseconds while NumPy is 223 microseconds. So that is that's one of, or rather that's these are few of the advantages of NumPy. I don't think, other than numerical computation and speed, there is no particular advantage of NumPy over Pandas when you are doing data analysis. And these are the reasons why we use Pandas. So let's go to the next topic, which is creating data frames. Okay, let's see. So a data frame is like a 2D matrix. So this is a data frame. The equivalent in NumPy would be a 2D matrix. We can perform, this has a lot of features, like if we look at pd.dataFrame, it has a ton of features. It takes in the data, index, columns. You can perform many operations on this. Okay, let me get rid of these. So we can load the data directly like this one from a CSV. We can also create from scratch. Like, how do we create this table from scratch, like a custom table? So suppose I want columns. For example, I want a name column and an age column and a profession column. We'll set some random data, like let's say Priya, age is 24, and then profession is like a web developer. Let's call it web dev. And then we have Rahul at age 30, and he's a blockchain dev. And then let's take only 3 columns just for just to keep it short. And then maybe while age is 40 and manager, let's say. So how do we construct this table in Pandas? So we have like 2 methods. Like we can do it 2 ways. One is we can stack in rows one after the other, or we can stack columns one after the other. So there is row wise and column wise. Let's look at row wise ones. So before pd.dataFrame, let's create our records. So we can create records using standard Python lists, or we can use NumPy arrays. So we can do something like, since it's a record, I can just copy directly this data. Oh, okay, this has to be strings. So it will basically be a list of lists, 2D lists. So something like this. Then I do this, and then we do this. And then manager. So this is our row data. Now if we do a df for short form for data frame. We do a pd dot data frame. What is the thing? We have data, which is our data. Let's pass the data. Let's call it rows. And then we have to set our columns. So we have to create our columns. Let's call it calls. And we create a column array with this exact same thing. We have our name, age, and profession. We pass this to the columns argument. Let's check our data frame, and there you see we have our own custom table. We can replace this instead of numpy rows. We can use something. We can use. I think it's pd dot. No, it's np dot array. Will this work? No, I guess it should be within the. Should be an array of numpy arrays. Create this. NumPy has no attribute array. Oh, okay, so guess it's small. Yeah, there you go. So we can create using NumPy arrays as well. Let me see. I think can we do an outer NumPy array? Yeah, we can. We can do a NumPy array of NumPy arrays. So this is row wise. Now if we look at column wise. So we want to stack these columns separately. So we can use standard Python lists, or we can use Pandas series or even NumPy arrays as well. So we use we use actually not it's not Python arrays. We use Python dictionaries. Columns, and we create name. This is our column name, which is the key value, and the value is value is all these three values vertically. So what we can do, since this is kind of getting painful, we'll do it slightly. I can do a multi-select here, and I will paste them here, comma. So the key and the value is the list of names, and similarly we create list of ages, which is let's just take 24, 30, 40, and then we create list of professions. We do I guess this is tricky. Okay, let me just copy. I think we do web dev, then we have blockchain dev, and we have a manager. So we have our columns. Now all we have to do is do something similar. We do df, we add the column data, and we already have columns in this in this key value pair. So we just have to run it, and this is the other way. We can also use, if I'm not wrong, I think we can use np.arrays here as well. Yes, we can use numpy arrays. We can do even we can do, I think, pd.series as well. This is Pandas series. This should work ideally. Yeah, that works. So we can do Pandas series. I think we can do Pandas series here as well. pd.series. Now the reason why we can do this way instead of plain Python arrays is pd.series have its own custom methods, so we can make use of those custom methods as well. So yeah, we can use pd.series as well. So that is how you can create our own custom data frames. Let's see. Okay, now so we know how to load data from Pandas, right? So if we want to quickly see the if we want to quickly get an overview of the data, we have methods like head. So head, if we look at the documentation, it says return the first n rows. So if we don't specify any value, the default is 5. So if we just do a head, it gives the top 5 rows, so 0 to 4. If I specify, let's say I want top 50 rows, I'll get the top 50 records. Same, there is a method called tail. So if I do tail, it will give me the bottom 50 rows. So you see, this is 1,067,370. We get the bottom 5 records, and then if I do a bottom 50, I'll get the bottom 50 records. Again, super convenient. Let's say I want to let's see. Let's say I want to do if I want to quickly get an overview of this table, we can do df.info. It will give me a summary of the table, like how many columns are there, what data types are there, how many missing values are there. These are all non-null. So this is a table overview, it's saying the memory used is about 65 MB. So this is basically table summary. Now if we want the table data summary, if we want to know what is the summary of the data that's in the table, we can use something like describe. It gives the descriptive stats of this table. Descriptive stats meaning the whatever numerical values are there. So suppose so if you see the numerical values in this table are quantity, we have price, and we have customer ID, which is pretty pointless, but you can ignore customer ID. But if you see the quantity and price, we get the count, how many quantities are there, then we get the mean of this quantity, we get standard deviation, which is the you can say the spread of the data on the graph, we'll see in the upcoming sections. Then you get minimum value, which is the minimum value in quantity, which is -8. So there is a -8 in minimum. There's a 25th percentile, 50th and 75th percentile. So if you how do I explain this? So if you do a box plot, we will see these 3 measures, 25th, 50th and 75th percentile. We will look at this data in detail later on, and we get a max value. Max is 8, which is quantity, and same for price as well. You get all these 3, and this this is summary of the numerical data in our table. So if we want to get the summary of the string values, like the categorical data, what we can do is something like, let's see, what is that? Yeah, we have to use the argument include, and we have to specify the data type as object. That will now consider all the string values as well. So if you see the stock code, turns out it's not a numerical value, because you see here there is a letter at the end, so it's a categorical value. So it's saying there are these many values of stock code, obviously, and then there are only 5,305 unique values of stock code, and the description there is 5,698, invoice date. So these are all non-numeric values, country, and then the top and frequency. So unique top, wait, I don't remember what top is, but frequency is like yeah, actually I don't remember what frequency is as well. I think frequency is number of times. Yeah, I don't remember frequency. I'll update this in probably in the next class. But this is basically how we'll see categorical data summary. What else? So that's the basic overview of Pandas. Now, okay, let's look at the CRUD operations. So CRUD operations, CRUD and filter ops in Pandas. So CRUD is basically create, read, update, delete. So this is the database naming. So it's basically like how can we create, and this is CRUD on, by the way, this is CRUD on columns. So how can we create a new column? How can we read or access columns? Then how can we update or modify columns, and how can we delete columns? So we'll look at we'll first look at reading the columns. How do we access columns? So we'll take the same example, which is we'll take this one. Now, if I want to access or rather, how do I see all the, if I want to just get a list of all the columns I have, I can do something like df.columns. That will give me all the columns present. Or I can do something like the same, there is another method called df.keys. It gives the same, it's the same functionality. So I'll get the list of all the column names present. Okay, now if I want to, suppose, give me a moment. So if I want to say, if I want to access a particular column called price, let's say I want to access price, I just have to pass the column name, and that will give me all the price values. If we, by the way, if we look at the data type of the original df, it's of type data frame. Let's look at it here only. Type of this df is called Pandas core frame data frame. Now, if you look at the type of this column, what is this column made of? It is of type series. So a data frame is nothing but a stack of series, like a series of, okay, this is getting a series of series, type series stacked horizontally. That is what a data frame or a table really is. So there are, so if we looked at data frame, what else? Yeah, so that is how you access a column basically. Is there any other way? No, that is it. So let's go to reading. So we have read it. So there is something called lock and iLock, which will come. It will be more relevant when we do the row level operations. So since we have done the access, let's check update first. So if I want to update column, so if I want to update the column name, so what I have to do is I do a df dot rename. Let's look at the documentation. Mapper. So rename takes a map of key value pairs. So we can do something like we create a map, and then if I say if I want to let's see, if I want to rename this customer ID to customer underscore ID, I don't want any spaces in this one, so I can specify the key and I can specify the value as customer underscore ID. I make it all lowercase. Okay, now if I do a df, okay, let me see what this gives. This gave nothing. This gave nothing because we have to specify the access. Access equal to, you remember, right? The horizontal is access 1, vertical is access 0. Now if you see, it changed the column name, it renamed the column name. Now we can do the same, we can do actually multiple, we can modify multiple columns at once. So if I say I want to change this as well to quantity as well to lowercase, so I can do something like quantity colon, let's change it to this one, and if we see the value, it changes. So quantity also changed to lowercase. So this is how you can rename multiple columns at once. Now, do you think this modified the actual table? You see, if I check the original table, it is still the same. It did not affect the changes. So to affect the changes, what we have to do is we have to do something called in place. So you see this one, in place. In place, whether to modify the data frame rather than creating a new one. So by default, these methods give us a view. They don't give us they don't modify the original data. So what we have to do is we have to set in place equal to true. So once we did in place, you see the data frame, the original value also changed. There is another way to modify this, which is basically by, let's change a different column. If I don't specify in place, all I have to do is just reassign reassign this view to the original data frame. So I change this description to lowercase. Okay. So the description changed, but the original is still the same. So to change the original, what I have to do is I have to assign the original data frame to this view. Now if we run this one, you see the original also got changed. So that is how we can update, we can modify the column names. Let's look at deletion, how we can delete some columns. delete columns. So we have df dot drop. Drop is the method used for deleting. Labels, index labels. So I think this one uses drop. Let's say I want to drop the description because it really doesn't make any sense for me. So if I drop description, or rather let me just set, let me just give the label as it is. We'll see what happens. It is throwing an error, and I think, yeah, access is not found. So we'll have to specify the access, which is 1. And as you can see, it removed the description. Okay, there is one more thing. We can do all these operations, even rename as well. We don't have to specify the access. If we don't want to specify the access, we can just say, you see here there is an argument called columns, alternative to specifying access. So if you don't want to specify the access, you just have to give columns. So if I suppose I want to drop the country, because let's just say I drop the country. You see it dropped the country. It dropped the country column even though I didn't specify the access. The same thing applies to rename as well. If you see the rename documentation, it also has a columns argument. So again, alternative to specifying access. So if you don't want to specify the access, you can just set the name to columns, like just like this, and remove the access, and this will still work. This will still work. So that is dropping. Now if I want to drop multiple, let's say I want to drop, oh by the way, this does not change the original. Again, you want to change the original, see the country is back. You have to specify the in place true, or you have to reassign the data frame. I won't be doing that because we'll be playing with this data for the row level operations as well. So you can play with those options. You can check this in place true. Now we can drop multiple columns as well, if I'm not wrong. I think we can drop country, and let's say I want to drop description as well. And let's say I want to drop stock code as well. As you can see, we can drop multiple columns at once. We can delete multiple columns at once. What else? Yeah, I think these are like the common operations for deleting columns. Now let's look at how we can create new columns. So let's check our data frame. So if I want to create a new column, all I have to do is I can set something like new column, and for now I will assign the quantity column as the new column. I will reassign, like I'll create a duplicate of the quantity and I'll call it as new column. Now if you check our data frame, you see here we have a new column with exact quantity values. So that's one way. I can do something like this. I want to have this new column as quantity. Let's call it as quantity plus 10. So this is basically the existing quantity column plus 10. I'm just creating a new column called quantity plus 10. So you see here the new column is obviously there because we reassigned this to the original one. And you see here there's a quantity plus 10, which is basically 12 plus 10, and then 48 plus 10, 58. So we can manipulate based on this. I think we can extend the date as well. Let's try date plus 7. So let's push the dates 1 week from the invoice date. Not sure if this will work, but I think this should work. No, it's not. What is the issue? Can only concatenate string, not int to string. Okay, I think they are not in the right date format. Wait, is it dot date time? Okay, okay. This format is slightly different. Wait, let me just check the. It's a series dot. Take it the 0. It's a string. Okay, we'll have to convert this to date time format and then do the operation. So again, just like I showed you, we can merge two columns. So we can do something like this. Let's just say I want to do something sensible. Okay, we'll do a quantity times price. Quantity times df price. So we can take these two columns and multiply them and to get the result. So let's see. Okay, it shouldn't be date plus 7, but fine. I guess that's fine. So you see, there is a date plus 7, which is basically quantity times price. So that is how you create new columns. Now, if you want to give your own values, you can do something like my vals and then assign your own values. Say something like for do a for loop for I in range. Now we have to consider all these values. So if we look at the df dot shape, what is our shape? Our shape is almost 1 million to 11 features. So 1 million rows, 11 columns, right? So I want all these 1 million rows to have values. So we'll go from, I can access the tuple. So that's basically a tuple. So I'll access the first from, I'll give it from the range. Yeah, so the range will be this will be the range. Now if I press this and if I check the data frame, you will see here it has my values ranging from 0 to these number of a million values. So that's how you can create your own, you can assign your own values to the column that you created. What else? Am I missing something? I think that is it. That is all there is to column CRUD. Let's look at filtering. So in this case, if I suppose want to, before that, let's clean up the table. This is a bit messy. df dot drop. Let's drop all the new columns. New col quantity plus 10, date plus 7, and my values. I think these are the unnecessary columns. Let's do a drop. Let's do in place. What is the issue? Not found in access. Okay, I have to specify the columns. Okay, let's check the df, and we have our original data frame. So suppose I want to get all the records which have quantity less than, say, 5. If you have seen my NumPy classes, you will see that this works very similar to NumPy. We create a Boolean mask kind of thing, and then we pass it to the original matrix, which is the original data frame in this case. So if I say df, which is basically quantity, okay, 1 second, quantity, and I want all the values less than or equal to 5. So you see, it's getting us a list of, which is basically a Pandas series. If you check the type of this, it's a series. So we get a series of Boolean values, and these are positional values. So all the values that are true, it will accept those, and all the values that are false, all those records will be rejected. So if we pass this mask, this filter to our data frame, we will get, you see, 14th, 16th, 21th, all the values that are less than or equal to 5 quantity, which is 3, 3, 4, 2, 3. So that's how you do filtering. And you can do, again, obviously you can do you can specify multiple conditions as well. So you can say if it's quantity is less than 5, so add clarifying braces, and let's say price is also less than 5. df price less than or equal to 5. Oh, sorry, I didn't specify the, wait, where is the closing? I have to specify the clarifying braces. Yeah, so you have to specify the clarifying braces, otherwise it will give wrong values. So you see here, quantity is also less than 5 and price is also less than 5. I can say something like, instead of and, I can give an or as well. So I think or is just a single pipe. So you see here, it shows either one of these options. So if quantity is less than 5 and price is less than, so in this case it gave quantity 48, price 2.10. Okay, so in the third record, since price condition satisfied, so price is less than 5, it kept this record even though the quantity is 48. I mean, you know how our condition works, right? So again, fourth record has price 1.25, so that this condition satisfied. So that's how you do multi-condition filtering in columns. So I think that's all there is to column CRUD. Now if we look at CRUD on rows, we have so let's see, again, create rows, access rows, update or rename, update rows you can say, and delete rows, we can drop rows. Let's see, let's check our data frame. Okay, on rows as well, there is on columns we access using these column names, right? And rows we access using these indices. So if you want to check our list of indices first, let's see how we have, let's see what we have. We have indices ranging from 0 to around this 1 millionth mark. And if I want to access one of my indices, suppose if I say I want to get the first index, I get 1 on 1. Why are we getting 1 on 1? Because our indexing is integer based indexing, which is our standard Python indexing, 0 to whatever 1 millionth mark. Now one of the advantages that we discussed that Pandas have is we can give custom indices, right? So what if I want to provide custom indices to this? So let's check the type of this index. What is this? What is the data type of this index? It's a type range index, and if we let's see, let us assign, let's take the condition where we give I don't want to start the indexing from 0, I want the indices to start from 1. So let's say I give I in range 1 to which is our shape, df.shape total values. We do a +1 because now we jumped the index, right? So we do a +1, and if we want to, perhaps you forgot a comma. Oh, sorry, is it comma? Now if we do a df.index, yeah. So let's check our data frame now. You see our indexing changed from 1 to 1 millionth mark. Now in this case, we'll have a kind of a problem. So previously we accessed our index 1, we got 1. Now if we access our index in this first position, let's see what we'll get. We'll get index 2 because we shifted our indices, right? This can be a major confusion. If you see, this can be quite confusing if we don't check the type of index we have. For that reason, Pandas has two special methods called ilock and lock, which are basically ilock is for implicit indexing, which is Python based indexing, which is basically integer based 0 to n, and lock is for explicit label based indexing, which is all your custom. So right now this 1, 2, 3, 4, these are not exactly integers. These are actually labels. You should not consider them as integers. You can almost think of them as string numbers. Just think of them that way. These are not exactly integers but labels. That's the correct way to look at them. ilock is basically integer locator, and lock is label locator. We'll come to this one, but before that I just want to show you floats as well. Let's set float indices. If I want to set float indices, I think this should do the job. No, float object cannot be interpreted as integer. Okay, this one still no. Okay. Change this to float. Now if I check df.index, you see all my indices got changed to float values, and we have float indices. I can similarly set integer indices as string indices as well. So let me take a small sample since we only have 26 characters in English. Sorry. Yeah, df dot head. Let's take top 5. And if you see our sample, we currently have float indices in this sample. Now, if I change these sample indices from floats to strings, so I'll do sample dot index. So I have 5 indices. Now I assign float values, string values, say A, B, C, D, E. Now if we look at our indices, we have strings, and if you look at our sample, you see our samples are our indices are A, B, C, D and E. We can right, so the other impressive thing about NumPy is we can create any one of these columns. We can turn these columns into our indices. So suppose if I do let's do it on the sample, sample dot set. I think if I'm not wrong, it's set index. It is set index. So set index takes keys as the argument, which is basically it is asking to specify which column you want to convert it into an index. So let's take stock code as the column. Let's not do in place and stuff for now. We'll just see set index. We might have to do in place. Wait, place true. If we check sample, you see here the stock code shifted from there to here, and our indices changed from A, B, C, D, E to stock code. If I want to now access one of these values, so let's come to access now. Access records. Let's begin with this one. So so you can do something like sample. I want to access the record with this stock code. So I can specify the label. Let's see what happens. This will actually throw an error. This will throw an error because this is an explicit label based indexing. Now let's come to the lock and iLock part. We have our standard this one, our data frame. Let's do a reset index. Reset index is basically reset the index of a level of it. So we are basically resetting this data frame to the original 0 to 1 index. So if I do a reset index, and if I have to, we'll see what happens. If I currently our data frame, if you see our indices are floating values, right? If I just set a reset index, you see we have a special column called index. What Pandas does is it does not discard the indices by default, because if we create custom indices based on our column value, we'll be losing our data, right? So it by default appends this index, these indices values as a separate column. Now, if we don't want to do that, what we have to do is we have to what is the documentation? Yeah, if we don't want to do that, we have to set drop to true. So this drops the old index column. You see here, do not try to insert index into data frame columns. This resets the index to the default integer index. Now if we do this, you see our indexing got reset to the original 0 to n Python based indexing. Now let's try to access some column. So you can do something like df0. If I do df0, what is it saying? Key error. So it's not allowing. What we have to do for getting the 0th column is we have to do an ilog, which is basically called implicit indexing or Python based 0 to n indexing. Now if we do this, we get our record. So you see we have invoice, stock code, description. If we look at the type of this, oops, one sec. It's a series. So we can do something like, we have a series of values, which is basically our single record, the first record. And if I want to get a value from this record, I can do something like invoice data, and I'll get the invoice date, and I'll get the exact value. So that's the really convenient part. That's how you access implicitly. If I want to do an explicit, there's something called explicit indexing or label based indexing. So we can do something like lock, and if I do a 0, let's see what happens. It is throwing an error. Key error 0, so it's basically saying it's not able to find. With this one still 0. Okay, so wait, this should work. So the 0th value is in explicit indexing. It is the first column, because in explicit indexing everything starts from 1 to n, not 0 to n. And you can also if we look at ilog once again, in ilog, since it's Python based, we can do a negative indexing. I can give -1, then it will give me the last row. So if you see here, the invoice ID is 581587, which is this one. Stock code is post, description is postage. So since ilog is implicit or Python based, you can do a negative indexing on this. But if we look at explicit indexing, you cannot do -1. And the reason is because there is no label called -1, right? For that you will have to get the exact record value, and since it's a 1-to-1 match, you will get the exact. You'll have to know the exact index value for that. What else? Okay, so we are checking lock, ilog. I think we checked renaming indices. Let's look at slicing. If we use our standard ilog method, we can do something like rows and columns, right? The syntax is basically rows, columns, right? So if I specify all of them, so this is basically 0 to the last 0 to the last row, and and the first to last column. And if I want to just get the first 5 rows, so I can say 0 to 5, and all the columns. I'll get the first 5 columns. Okay, since we did not do reset in place, I think I have to give in place as well. 1 second. Yeah, we have to give an in place for reset as well. In place true. We did our in place. Now if we access, we have our 0 to 4th column. That explains, okay, that was the reason why it was not working. 1 second. So if we do a lock 0, see, lock 0 also works. So it's a 1-to-1 match. Okay, we didn't do an in place, so that's why we were getting an error there. So now, so lock also works with 0. Since 0 is an explicit label, we'll get the exact 0th value. So that was that. Anyway, by the way, that was a small digression. But let's come back to labeling. So yeah, that's how you get the first 5 rows. And if I want to get the first 2 columns, I can do something like 0 to 2, and we get the first 2 columns. Now, one thing to remember is columns in ilock, or rather the end value in ilock is implicit, and end is exclusive, which means the end value is excluded. So we only get 0 and 1 if we are in a 0 to 1 based situation. So if we want actually the second index as well, so we'll have to set 3. But if we look at lock, if we do a 5 to 3, so it's basically throwing an error. Let's see, why is it throwing an error? Cannot do slice indexing on index with these indexers of type int. I think in lock I'll have to specify the columns explicitly. So if I want the first 3, I'll have to do invoice stock code and description. And so you'll have to, okay, in lock you cannot do slicing for columns. You'll have to specify that explicitly. The number of columns you want to access, or you can do one more way. You can do slicing, but you can do something like this. I want the columns from invoice to description. You can do this kind of slicing and it will still give. So let's say I want invoice from invoice to invoice date. So I can do this type of slicing as well. Suppose let's take the sample. So we have our sample. Now if I want to do a slicing on our sample, how do we do that? So df.ilock, can we do an ilock here? We cannot, or can we? Let's see. So that seems to be working. Okay, it's not df, it's sample. That is working. Now if I want to get from 0 to 3, that is also working. So we can do a slice on the label based indexing as well. And if I want to get the first 3 columns, I can do 0 to 3. If I want only 2 and 3, I'll get only the quantity as well. Can we do this on lock as well? This will throw an error because lock only supports label based, right? So you cannot access integer based labels on this. So what you have to do is you have to specify something like this to say this one, this value. So these are the stock code start and end values, and I want to specify all the columns from indices to countries to country. That works. So in lock you can explicitly specify the label ranges, and you can set ranges from the labels. Pandas will automatically check the start and end values. Now what if I want to cherry pick only a particular set of rows and particular set of columns? Suppose let's take the data frame. We have our df. So if I want to access the first, third and say fifth rows, what I have to do is I have to pass the 0th. For third I can say 2, and for fifth I can say 0, 1, 2, 3, I can say 4, and all the columns. So you see I got the 0th row, I got the second row, and I got the 4th row. Now what if I want to cherry pick on columns as well? So I want only the invoice, I want the quantity, and I want the price. Interesting. Okay. Okay. So this is ilock. So we'll have to use the indices. So I want the 0th, 0, 1, 2, 3 third index, and 4 fifth index. So that's how you can cherry pick in ilock. Now if we use lock, then we'll have to specify the labels explicitly, something like these are the labels. For columns we just use them, and for rows I'm going to use the same labels because these are the indices, so these are the exact label names. If you see, okay, one important thing I think I missed in slicing for lock. For lock, the end is inclusive. While ilock, it is excluded. We'll look at the slicing thing in the next one. So for now, if you want to cherry pick on lock using explicit labels, I will get the exact values. I'll get the exact 0th value, I'll get the exact second value, and I'll get the exact 4th value. You see here, this makes more sense if we are using a 1 to n indexing. So let's see, let me do a 1 to n indexing, and then we'll check the above. You'll see the difference properly. So df dot index, I'll change the label from I for I in range 1 to df dot shape 0 plus 1. We do a plus 1 because we're starting from 1. Now if you check the df, we have our indexing starting from 1. Now if we look at this exact same thing, this will throw an error. So df dot lock 0 to 4, we saw that this is explicit indexing, right? And there is no explicit index called 0. So this will throw an error. So what is it saying? 0 not an index. So to get the exact index, now we'll have to pass the first value as 1, and if we want the third value, we have to pass exactly 3. And if we want the fifth value, we want exactly 5. So that's how you get. But if we check ilock, in order to get the first value, we still have to use 0. If we use 1, this is yeah, let's use all columns. I don't think we need to specify for this example. So you see here for ilock we are getting the index as 2. Third value we are getting fourth index, and fifth value we are getting fifth value we are getting index as 6. So in order to get the first value we have to pass 0 for ilock, third value we have to pass 2, and fifth value we have to pass 4. So that will give us the 135. So I hope that was clear. Now let's look at the lock slicing. So if I slice the TF using lock, so I want the first 5 values. If I want the first 5 values, and if I set 1 to 5, you see here I'm getting the fifth value included. But if I use ilock, which is basically Python or implicit indexing, if I do a 1 to 5, you see I'm getting 2 to 5, which is basically first value is 2, second value is 3, third value is 4, fourth value is 5. So if I want the first 5 values, then I have to set 6. That will give us the first or rather values. If I want the first 5 values, then I have to set 0 to 5, then we'll get the first 5 values. That is so that is slicing, that is cherry picking. I think that was kind of clear. I hope that was clear. And we have seen negative indexing, right? So you can do negative indexing in ilock. So if I do this, okay, let's say -1 to, I do -5. Rows, columns. Interesting. -1 to. Start, stop, step. Okay, we have to give the step size as well. Start, stop, step would be -1. Yeah, so we have to give the step size as well, because we are using negative indexing. So it will give us the last 4. So -1, -2, -3, -4. We know that ilock, the stop is or rather the end is excluded, right? So the syntax is something like start, stop, or rather start, end, step size. That's for rows. And for column, again you have start, stop, step. So if I want the last say 3 columns, suppose, and if I do a negative indexing, so -1 to -1, -2, -3, yeah, so I'll set -4, and I'll increase the step size to -1. You'll see I'll get the last 3 values, which is let me just print this one just for. So you see here I'm getting country, which is -1, customer ID -2, price is -3, -4 is excluded. So that is how you do it in ilock negative indexing. But if you do it in lock, it doesn't work. There's no concept of negative indexing because there are no negative labels itself. There is no, you don't have there's no -1 label, right? There's no -5 label. So that is why this negative indexing only works in Python based or implicit indexing, and explicit indices, there's no concept of negative indexing. We have checked column values as indices, right? So we have already covered that topic here. Where is that? Set index. So I can I can take any column as an index value, and then access values based on these indices. So that's basically column values as indices. We covered that as well, and I think that covers the CRUD operations on rows. So let's look at filtering. Okay, this video is getting too long. I'm also losing my voice anyway. So if we look at filtering, df again the let's see. df dot ilog, if I do something like df, okay, let's see what is our data frame. So if I do df quantity, again we'll take the same example, quantity less than or equal to 5. See what it does. It gives allocation based Boolean indexing on integer type is not available. So this filtering is not possible. Let's see. Which kind of makes sense, because there's no point filtering on indices, right? We only want to filter based on columns. So there's no filtering based on I don't think there is row level filtering. Is there? Yeah, I don't think there is row level filtering, but I will, if there is one, I'll cover that in the next section. I don't think there is row level filtering. My memory is a bit hazy, but yeah, I think there is no row level filtering. We can skip that for now. Let's look at some miscellaneous methods. So Pandas has some special functionality, like something called so you have df.n unique, there is df.unique, which gets all the unique values. We have df.count, which basically counts the number of rows. I think for now, I think these are the three special methods we'll discuss. There are like a ton of features, but count. Yeah, we'll look at these three for now, since the video is getting too long. Let's see. So if we want to get the unique values from the data frame, this will not work. If we want, we can only get from a series. So if I want to get all the unique values present in the say stock code, I want all the unique stock codes. Series object has no attribute un. Okay. unique. If we do it on df, it's still not available. If we do it on series, we will get all the unique values present in the stock code field. Stock code column. If I want to check the count of unique values, I can do n unique. So this will give me all the unique values, or rather, wait, is it n unique? Yeah, it is n unique method. So it will give me all the unique methods in, so all the unique values present in the stock code column. Now, how do we know these are the only unique? Let's look at the count. So if we look at the count, we have about 1 million, right? And only 5,000 are unique. So that's how you can check the unique values present. And the one thing is n unique works on the entire data frame as well. So it will give us all the number of unique values present in every column. So invoice has about 53,000. Stock code has only 5,000 unique values. Description again 5,000. So that's basically the idea of unique and n-unique and count. Yeah, I think that is it. If I missed anything, or rather, I don't think I missed anything for this class. So yeah, I think that's it. And yeah, I hope that was useful. I'll see you in the next one.